Hi and welcome to Computing Fundamentals 1. Today we will speak about matrices and we will focus about the definition and the arithmetic operation of matrices. Then we will speak about the transposes and the powers of arithmetic with regard to matrix and 0 and 1 matrices. I want you to pay attention for matrices because they are very useful in computer science, and we use them in many applications, most importantly in data analytics and machine learning, because matrices are the foundation of data analysis and machine learning. Now we know from computer science that a matrix is a two-dimensional array, but fundamentally matrix is a rectangular array of numbers, where we have a matrix with m rows and n columns, and we call it m by n matrix. For example, if we have a matrix with 3 by 2, this means we have 3 rows and 2 columns. So this notation where we have m and n are positive integers will give us an array A or a matrix. Each item in this array has a location or an index, so we can access it based on the row number and the column name. So A11 means we have an item located at row 1 and column 1. Also we have A22, which means it's located at the second row and the second column. Now the first arithmetic operation we want to study is basically addition. So if we have a matrix A and B, where both of them are m by n, so they have the same basically number of rows and the same number of columns, then the outcome of this addition, A plus B, is basically the addition of each item in the same locations. Add A of 1 and 1 to B of 1 and 1. So 1 plus 3 equals to 4, 0 plus 4 equals to 4, minus 1 plus minus 1, minus 2, and so on. Now the second operation is multiplication, and by multiplication we need to focus a little bit more than the basic arithmetic multiplication we use in digital numbers. So if we have a matrix A where the dimension of this matrix is m by k, and we have another one which is another matrix called B, and the dimension of this matrix is basically k by n, the product, now pay more attention to this, the product of A and B denoted by A capital B capital is basically an m by n matrix, and the reason for that, we will multiply the row from A by the column from B, or otherwise we multiply the column of A by the row of B, and so on. So in this example we have two matrices. The first one is 1, 2, 3, 4 rows and 3 columns. The other one has 3 rows and 2 columns. The outcome of this matrix is going to be 4 rows by 2 columns. So as a notation of or an illustration of the matrix multiplication, if we have A of I and J, and B equals to B I and J, and we have A1 and 1, A1 and 2, A1 and K, and B is B1 and 1, B1 and 2, and so on. The outcome is going to be C1, 1 in the first element, and Ci of J is equal to A of I, 1, B1, J all the time, and also plus A of I, 2, B2 of J all the time. To understand it, let us just have a simple example. We have two matrices. We have the first one with 2 rows and 3 columns, and the second one is basically 3 rows and 2 columns, and now we want to find the calculation of these matrices. The rule is we multiply the rows by the column. So let us take the first row 1, 2, 3 and we multiply it by the column 8, 10 and 12. This is going to be 64. Now if you look here, we can take the second row from matrix A and multiply it by the first column of matrix B, and this is going to be 139. Be careful because basically the product AB is not equal to the product BA. The identity matrix, and with identity matrix we have a matrix of order n with a dimension m by n. The matrix I, which stands for identity of n, is basically the sigma of I and j, and that sigma is equal to 1 if I equal j, and sigma equal 0 if I is not equal to j. And this is very simple because you go to the matrix and you find whether I and j are equal, so this is basically the diagonal of the matrix. Now the power of a squares matrix can be defined when A is n by n matrix and we have A of 0 which equals I of n, or A of r is basically A multiplied by A multiplied by A number of times. Now with the transpose we have a matrix A and this is with the dimension m by n, then the transpose of A donated by A of to the power t, or A transpose, is n by m matrix obtained by changing the rows with the columns of that matrix A. So in this example we have 1, 4 as the first column and 1, 2, 3 as the first row. When we transpose it, we just basically transform it anti-clockwise. So 1, 2, 3, which is the first column here, became the new column in the new matrix. The square matrix A is called a symmetric if basically A equals to A transpose. And this A is symmetric if A of I and j equal A of j and I for all values I to j. Finally, the 0, 1 matrix, it's basically a matrix. All of those its entry are either 0 or 1, and we call it 0, 1 matrix. And we will use it in fundamental too. So this is basically an algorithm operating on discrete structure represented by a binary outcome, whether 0 or 1, defined by B1 and B2. It is 1 if B1 equals to B2, 0 otherwise. Considering the OR notation, B1 or B2, it will be the same 1 if B1 equals to 1 or B2 equals to 1. Now the first is basically when both conditions satisfy, which is the AND operator, and the second one is the OR operator. If we have a matrix called A, which is A of I and j, and B of I and j, and both with a dimension m by n, the join of A and B is the 0, 1 matrix with the I and j entry such that A of I and j or B I and j. Now this join of A and B is denoted by the notation A or B. The meet is basically the of A and B is the 0, 1 matrix with basically the AND operator, where we have A of I and j and B I and j, and the meet of I and B is denoted by A and B capital. So let us take an example. If you have look to this matrix A, where we have 1, 0, 1 in the first row, 0, 1, 0 in the second one, and now we want to find the join of A and B. And the join, we take the OR notation in each respective location in both matrix. So 1 or 0, 0 or 1, 1 or 0, 0 or 1, 1 and or 1, 0 or 0, and we will find the meet of this matrix, which is 1, 1, 1 in the first row and 1, 1, 0 in the second one. Now the meet of A and B is A and B, and this is basically 1 and 0, which is basically 0, 0 and 1 is basically 0, and so on. The Boolean product of 0, 1 matrix, where we have A of I and J, is basically M by K 0, 1 matrix, and B, which is B of I and J, which is basically the N0 matrix with the Boolean product of A and B. And we always denote it by A dotted product or Boolean product of B. Now, if you take the Boolean product of A and B in this example, you will find that the Boolean product of A and B equals to the following, because you take now 1 and 1 in the first item, or 0 and 0 in the second item, and so on. If we have an A matrix, and it is a square 0, 1 matrix, and R be a positive integer, the R's Boolean power of A is the Boolean product of R factors of A, and we denote it by saying A basically the Boolean product of R with respect to R. And this is also be defined by A to R to be I of N. In this case, the Boolean product is well defined because the Boolean product of matrices is associative relationship. Now, to understand it, let us take the last example where we have a matrix A. For example, we have 0, 0, 1 in the first row, and we have 0, 1, 1 in the first column. So if you find A to the power n for all positive integers of n, we need to take, for example, A to the Boolean product of 2, and this is going to be A multiplied Boolean product of A one time. A of 3 is A of 2 multiplied by A, and so on. And these are the Boolean product of A. Thank you for seeing this video. See you in the next one.